Okay, welcome back. So today we're going to talk about more trigonometric graphs. So far the trigonometric functions we've talked about are sine x, cosine x, and tan x. We looked at the graphs for sine x. That's the snake, and cosine x. That's the cup. Right. So here I'll just kind of sketch those out quickly for you. So you're familiar with sine x between 0 and 2 pi looks something like this, right? And then cosine x is the cup, right? So from 0 to 2 pi, it looks something like this, right? And those really are the same functions. There's kind of an up-down motion. They're just shifted, with respect to one another. But we haven't looked at the tangent graph. And there are three other functions that we're going to look at. Y equals cosecant, y equals secant, and y equals cotangent. Okay, and so that's what we're gonna do today. Is we're gonna look at the graphs for tangent, cosecant, secant, and cotangent. Okay, so first of all, one of the ways of thinking about this is in terms of rational function. So it turns out that tan x is also equal to sine x over cosine x. So what we're going to do is we're going to use these sine x and cosine x graphs, and we're going to use this relationship to graph tangent of x. This is cosecant. This is secant, and this is cotangent. Okay, so that's how they're usually pronounced. So cosecant, turns out, is equal to 1 over sine x. Secant is 1 over cosine x. And cotangent, hopefully you see a pattern here, is 1 over tangent of x. So these are really just inverse functions of these three trig functions that we know about. Okay? All right. So basically our graphical strategy is to look at sine and cosine and then look at these relationships. So for tangent sine x over cosine, cosecant 1 over sine, 1 over cosine, and then once we have this one, we can look at 1 over tan. And so this is also equal to cosine x over sine x. All right, so actually we're going to look at this form. But that's what we're going to do today, look at these graphs. Okay, so I want to go over first our general strategy for this. Okay, so all of these functions can be written as something, a rational expression, right? Numerator over a denominator. Whether it's sine x over cosine x or 1 over sine x or whatever, right? So there's a numerator and a denominator. Basically, our strategy is first, if the numerator is equal to 0, that is a situation where you have 0 over some number is equal to 0. 0 over any number is equal to 0, other than 0 equals 0. We'll talk about that in a second. Then the graph y equals 0. Okay, at that point. And then our other thing is if the denominator equals 0. If the denominator equals 0, we know that if you have some number over 0, that's undefined. So if you have a number over 0, it's going to be undefined. And then what that means is that you graph a vertical asymptote. Right? So we don't want undefined values. So that means that we're going to have a vertical asymptote at that location, right? So for example, like it could look something like as you approach it, it could go to infinity or it can go to, minus infinity, let's say, something like that. One of those two options, something like that from that direction. Okay? Now, the only thing that, so we're going to just apply this to those situations. So this is we're going to look at the numerator when it's 0. And that's going to tell us when our graph is 0. And then we're going to look at denominator equals 0. That's going to tell us where we have vertical asymptotes. And then from the rest of that, we can kind of infer what the rest of it looks like. So one thing to be aware of, and especially this is, sometimes I like to have you think about more advanced math, which is that you have to beware. We're not going to come up with a situation, but you have to beware of what are called indeterminate forms. And the form that we would have would be like 0 over 0. If you have something that's like 0 over 0, then these don't necessarily apply. You have to use more advanced methods. So if you take calculus, you'll learn about this method called L'Hopital's rule, where basically you take the limit as it approaches, and there are various ways of dealing with this kind of indeterminate. If you want to look at, there's this function called the sinc function, which is sine x over x. As x approaches 0, it becomes 0 over 0. So that's, if you want to look that one up, if you're interested in this indeterminate form, you can look at this. So we're not going to deal with situations where you have this for r's, but that's just something to keep in the back of your mind if you end up doing this more later. All right, so let's apply our strategy. So the first that we're going to apply to is our tangent function. All right, so our tangent function, y equals tangent of x is sine x over cosine x. Okay, so let's break this up into two parts. So we'll have our numerator, which is a y equals sine x. And then we'll have our denominator, y equals cosine x. Okay, so let's do each of these in a different color. So let's do y equals sine x in blue. So let's graph what we know about sine x. So at pi, 2 pi, sine x goes to 1 and minus 1. This is y and this is x. And it goes like this. At pi over 2, it's 1. That goes to 0. Right? That's the snake. So it goes up to there. And then cosine, I'll do in green. Pi and 2 pi. And again, it goes 1 and negative 1. And it starts at 1, goes to 0. All right. So hopefully you remember those. So let's follow our strategy. So the strategy first was figure out when the numerator equals a 0. So when does... So sine x equal to 0, basically that's going to occur at where it crosses its axis. So we have this point, and this point. So that's at x equals 0, pi, and 2 pi. So what that means for our graph is that the graph y equals 0 at x equals 0, pi, and 2 pi. Right? So wherever the numerator is equal to 0, we're going to have zeros on our graph. And then for the denominator, we're going to do something similar. So when cosine x is equal to 0, that's what the denominator is. That occurs at 2 locations in this range from 0 to 2 pi. So that occurs at x equals pi over 2 and 3 pi over 2. All right. So what that means is that we're going to graph vertical asymptotes at x equals pi over 2 and 3 pi over 2. All right, so let's put those together. So we have our, this is going to be y equals tangent of x. Pi, 2 pi, and I'll put these points over here. This is pi over 2, 3 pi over 2. All right? Here, I should also write x and y on all these, but hopefully this is always going to be x and that's always going to be y. All right, so the first spot, let's look at these numerators. So y equals 0 at x equals 0. So we have a point there. X equals pi. X equals 2 pi. That tells us our zeros. Y equals 0 at those 3 points. And then we have vertical asymptotes at pi over 2 and 3 pi over 2. So that means that I'm going to draw these vertical dotted lines where the graph is not allowed to cross those lines. Okay? So it might not be entirely clear, but it starts at 0 and then has a vertical asymptote. So the question is, does it go upward or does it go downward? And so what you would look at first is in that 0 to pi over 2, the numerator would be positive and the denominator would be positive. So what you get is you get something that looks something like this. So it's going up toward positive infinity. In the second region, between pi over 2 to pi, you see that sine is positive, but cosine is negative. So that's positive over negative gives you a negative. So you come up from negative infinity. From pi to 3 pi over 2 is negative and a negative, so that double negative makes it positive. And then this last, you have a negative for sine, and the denominator is positive, so you get a negative like this. So that is what our tangent function looks like. All right. So there is something to kind of take note of, and it's the pattern. So we didn't kind of draw the whole thing, but it turns out that this particular pattern is a repeating one. So if we went farther, we would see kind of a repeating shape here. So you get this kind of shape that looks like this. All right, so it doesn't go quite flat. It's still a little slope there. But this repeating pattern every pi units or every pi radians, you get this kind of same shape that just kind of is stamped along, you know, from negative infinity to infinity. So that's our tangent function. All right, so that's what we're going to do. We're going to use that. Our next graph that we're going to do is the cosecant function. All right, and we're going to do basically the same exact idea. So cosecant is 1 over sine of x. So we're going to have our numerator, which is 1. And then we're going to have our denominator, which is equal to sine x. Okay? So if we look at this, we want to figure out where the numerator is equal to 0. And you can see that here, I'll use blue again. It's never equal to 0. And so since it's never equal to 0, that means the graph is never never touches y equals 0. Okay, so it never crosses that. So we don't have any zeros in that particular graph. So the denominator equals sine x. So we know what sine looks like. So we were looking at the zeros here, here, and here. And so it's sine x equals 0 at x equals 0, pi, and 2 pi. So that means that you have vertical asymptotes at x equals 0, pi, and 2 pi. So what does that look like when you put all of this together? So y equals cosecant of x, something like this. Pi, 2 pi. So we have, so actually let me do this in red so it stands out a bit. But we're going to have vertical asymptotes at 0, pi, and 2 pi. And it's not going to cross the axis. So is there anything else we know? One of the things we know is that sine x goes from 1 to -1, and it's 1 over 1 is 1. So we're going to have a point at pi over 2 here where it's 1, and a point over here where it's -1. And so in this first region, numerator is always positive. We have positive, so we should be going positive infinity. And this between pi over 2 to pi, it's also 1 over a positive number, so that should go to a positive infinity. And then in negative direction, we have also negative. 1 over a negative makes it go negative. And 1 over a negative in this region also is negative, so you go like that. So that is what the cosecant function looks like. Now there is two things that I want to take note of. One is the pattern. And again, it's a pattern that you see that goes from infinity to infinity. It's basically like you get these kind of U shapes that go on forever. One up, one down. A happy face and a sad face, just kind of alternating into infinity. The other thing is that sometimes you see books talk about this, which is that I'll put this in quote, kisses the sine function. All right, so if we draw the sine function on here, I'll use green, that's consistent, is that if you draw the sine function on here, the sine function will look kind of like this. I'll do it in kind of dotted line so it's not too confusing. Which is that you can see that there's this point, this is the sine function, where they just kind of kiss at the peaks and the troughs, but then they kind of go in the opposite direction. This one shoots off to infinity, this one kind of goes downward. This one shoots to infinity, it goes downward. So they touch kind of at those peaks and troughs. All right, so that's another kind of pattern that we'll see. Also applies to secant, which we're going to do next. All right, so hopefully you see the strategy. I mean, we're just going to do this for all four. So y equals secant of x, which is 1 over cosine of x. So again, we have the numerator is equal to 1, and we have the denominator equal to cosine of x. And so for the numerator, it's never equal to 0. So that means that there are no zeros on the graph. All right. And then for cosine x, we start here, go there. All right, so we go. So what we're looking for now is we're looking for zeros, and you can see there's a 0 here and a 0 here. So we have cosine x equals 0 at x equals pi over 2 and 3 pi over 2. Okay, so that means that we have vertical asymptotes at x equals pi over 2 and 3 pi over 2. Right, so numerator is always zeros, denominator is always vertical asymptotes. So we'll graph these together. Okay, so pi, 2 pi, pi over 2, 3 pi over 2. Okay, so our vertical asymptote, here I'll also put 1 and negative 1, that's going to be important here. So our vertical asymptotes are pi over 2 and 3 pi over 2. And again, it's a similar kind of pattern that you might guess before, is basically when cosine equals 1, we're going to have our graph is equal to 1, is equal to negative 1. Our graph is going to be negative 1 because 1 over 1 is 1. 1 over negative 1 is negative 1. So in this first region, it's positive, so that means it's going to go in positive infinity. Then it goes negative, so 1 over a negative is a negative, so it's going to go to negative infinity. Again, it's negative in this region, pi and 3 pi over 2, so that's also going to go to negative infinity at that vertical asymptote. And then it's equal to 1 here, and it's positive, so 1 over a positive is going to be positive. So that is what our secant function looks like. And again, there are two things to pay attention to. It's the same things as the cosecant, basically. It's our pattern, And again, I didn't draw it, but it turns out that, again, it's the same kind of like happy, sad pattern that you see before. Happy, sad, happy, sad, and it kind of goes on forever. All right. The other thing is, again, just like the cosecant function kissed the sine function, the secant function kisses the cosine function. All right. So here. So yeah, so the cosine function looks something like this. Do it as a dotted line. Yeah, so everywhere that you have a peak for the cosine function, it will kiss the secant function. And where you have a trough, they'll kind of kiss at the peaks and troughs. And that kind of goes on forever. All right. All right, we've got one more new graph, and that's the cotangent function. Okay, so we could do, we know the cotangent is 1 over tangent of x. And we know tangent of x is sine over cosine, so this would be cosine over sine. So we could do a tan x, but I think it's more clear to go through the same procedure with cosine over sine. And the reason is because basically this has vertical asymptotes. It goes to infinity, so you have to deal with 1 over infinity, which we could do, but I think it just is, you know, more fitting for this pattern if we just do cosine over sine. So let's do cotangent is cosine x over sine x. And we'll do the same thing. Numerator is equal to cosine x. And denominator is equal to sine x. And it's the same thing. So cosine x looks something like, all right, I did this a little bit sloppier than I should have, but hopefully you get the idea. So where is this 0? So we're going to have zeros on the graph at x equals pi over 2 and 3 pi over 2. All right. And then sine x is going to be zeros. We're going to have vertical asymptotes at x equals 0, pi, and 2 pi. Okay, so that's what we're going to do. So let's graph this. Cotangent of x so pi, 2 pi, pi over 2, 3 pi over 2. Okay, 1 minus 1. In this case, that is not that important, but we'll do it anyway. All right, so we're going to have zeros at pi over 2 and 3 pi over 2. Then we're going to have vertical asymptotes at 0, pi, 2 pi. And so in this first region between 0 and pi over 2, we have a positive and a positive. So positive over positive is positive, so it's going to go toward positive infinity. And then we have negative and a positive, so that's going to go to negative infinity. And if you follow that same reasoning, you get this. So that's our cotangent function. And again, is to pay attention to the pattern. And our pattern is basically kind of like this. That repeats every pi radians. All right. So I'm not sure exactly what, maybe how you would think this looks. Maybe like some sort of, I don't know, worm or something. I don't know, infinite worm. All right. So those are the new graphs. So let me do a summary. All right, so let's do a summary of these graphs. So y equals sine x. y equals cosine x, y equals tangent of x, and then we have y equals cosecant of x, y equals secant of x, and y equals cotangent of x. All right, so let's draw axes for all of these. These are going to be a little bit more sketchy. Like literally, these are going to be sketches. So on your homework, I scanned it as a PDF, and I've given you the axes, so you won't have to redraw all of these. But I don't want to spend forever trying to draw these things, so I'm sort of being maybe quicker than I should. All right, so let's draw these. Yeah, we'll just do different colors. So sine, looks something like this. The snake. Right, and cosecant x kind of kisses it. It has vertical asymptotes. Remember, it kisses the sine function, but then goes in the opposite direction, so -1 here. All right. Then we have cosine. Let's do that in blue. Cosine looks like the cup, from 0 to 2 pi anyway. All right, and then the secant function has vertical asymptotes at pi over 2 and 3 pi over 2. And again, it kisses the cosine function at its peaks. So it looks like that. All right. So really, if you look at these, sine and cosine are the same. They're just kind of shifted. Like if you shift this one to the left, pi over 2, you get a cosine. And just like if you were to shift this pi over 2, you get cosecant pi over 2 to the left becomes secant. So that's a pattern, because that's basically not a coincidence. And then we have tangent. Here, we'll do this in red. We have vertical asymptotes at pi over 2 and 3 pi over 2. And tangent looks like this. Okay. And then cotangent looks like this. All right. So now the thing with tangent and cotangent is they look similar. They have this kind of wormy pattern. But you can see that they're kind of wiggling in opposite directions. So this one kind of goes from bottom left up to top right. But then this one goes kind of from top left down to bottom right. Okay, so it's kind of moving in opposite directions, maybe kind of mirror-ish. Also, you do see the kind of shift where the asymptotes kind of shift over kind of pi over 2. All right, so that's kind of interesting. All right, so those are the new graphs, tangent, cosecant, secant, and cotangent. And hopefully you kind of see we're applying things we learned about vertical asymptotes to graphing these kind of graphs. All right, so there's one final thing I want to talk about. It is horizontal and vertical shifts. So your homework is basically graphing these with horizontal and vertical shifts. So I want to remind you that we have f of x minus h means it's a shift right h units. And if you have f of x plus k, that's a shift up k units. All right, so remember that if it's inside the function, that's going to be a left-right shift. And if it's minus, that's going to be a shift to the right. If it's plus, shift to the left. And then if it's outside, that's going to be an up-down shift. If it's positive, then it's a shift upward. If it's negative, it's shift downward. So generally the sign thing is kind of in opposite directions for the X versus Y. We've talked about that before. So let's look at something like y equals secant of x plus pi over 2. So if we saw something like this, that would be a clear indication that we have secant x, but we want to shift it left pi over 2 units. All right, so it's positive, which means it's the left and pi over 2. And it's inside the secant, so that's going to be a left-right shift rather than up and down. All right. So I'm going to kind of quickly draw the secant function to kind of remind us. So the secant function, pi, 2 pi, we have a vertical asymptote, and then we have 1 minus 1. All right, so if we're going to shift this left, so one of the strategies I think is always good if we're shifting this is to first shift the asymptotes. All right, so first shift the asymptotes. All right, so we originally had an asymptote that was at pi over 2, so we're going to shift that left to 0. And then this asymptote was originally at 3 pi over 2, but we're going to shift it to pi. And then we're going to look at other things. So we had this point at pi that's going to shift left to here, and so that shape is going to be down here. And then we had a point at pi over 2 that's going to get shifted left over here, and that's going to be up like this. Now, we didn't draw that other part, but we know that this pattern is kind of like a happy, sad thing, and there's going to be an asymptote at pi over 2. So this would be the graph of y equals secant x plus pi over 2. Okay, so that's how you would shift that left. So for these, shift the asymptote first. Okay, so let's do y equals, I'm sorry, I wrote that wrong, cosecant of x plus 3. So you can see that this is outside, so this is going to be a shift. I keep writing cosine. Cosecant of x up 3. Okay, so let's start with cosecant. So cosecant looks like this. I have a vertical asymptote, yep, at pi, and another one at 2 pi. And then I have a happy face here, and then -1, I have a sad face. Okay, so I have done this for a long time. I know the sine function really well, so I always think of the kind of kissing the sine function. So I'm sort of thinking about what the sine function looks like, and I'm just sort of drawing that. All right, so again, we want to shift it up 3. So how do we shift it up 3? So the strategy that I use is that I move the 0 axis. So I draw a new 0 axis. All right, and that's basically new. Maybe I should say x-axis, but it's not really x-axis. It's kind of a. I'll show you. It'll make more sense when I draw it. So our regular axis goes like this. All right. So if we're shifting it up 3, right, we have 1, 2, 3. Actually, I'm going to go a little bit higher. So my new axis is going to be x-axis is going to be shifted. So I draw a little dotted line, and I say this is quote unquote the new x-axis. All right. So You know, I don't know. There might be some math professors or math teachers that don't like that kind of terminology. That's just how I think about it. Actually, I'm going to need to go up a little bit more. And then I'm going to draw my cosecant from there, right? So these vertical asymptotes don't shift. They're still at pi and 2 pi. But then I'm going to go, before I went 1 above the x-axis, so this time I'm going to go 1 over the new axis. Actually, maybe I'll use a different color. Let's do red. And so I get the same shape, but above this. And before, this was 1 below, so I go 1 below, which happens to be along this 2 line, and then it's going to be something like this, right? And this gets closer and closer, but never crosses. All right. So that would be the correct graph. All right. The whole thing gets shifted up by 3. Okay. And then the last example I have is one in which we do both. So y equals yeah, let's try this one. Cotangent x minus pi over 2 plus 1. So for this, we have 2. So we're going to start off with the cotangent function, and we're going to go right pi over 2, because it's minus inside. And then we're going to go up 1. So let's start off with our cotangent function. So our cotangent of x looks something like this. We have a asymptote here and an asymptote here. It's 0 at those points. And we go up and go down. All right, so there are 2 things here. So let's draw a new axis. So we're going to go up 1. So we're going to go up 1. So remember, when we do vertical axes, we're going to draw a new x-axis. You don't have to write this down. That's just how I think of it. And then the other thing is that we're going to shift right by pi over 2. So we're going to shift these vertical asymptotes. So we had a vertical asymptote at pi. So if we shift it over at pi over 2, we're going to have a vertical asymptote here. And we're going to have this vertical asymptote shifts over. So we're going to have a vertical asymptote at 3 pi over 2. Okay? So then we know we also have zeros here. So those get shifted to the right and up. So this point is going to be right there. And also this one was here. It's going to go right and up. We're going to over there. So we're going to have something that looks like this. Here, I'll just draw for fun, but it also goes like this. And then from over here, we're going to have, because I know what that pattern looks like. So our graph should look something like this, where it gets, okay, where you shifted both left, right pi over 2 and also up 1. So most of your homework is these kinds of problems. I'll give you a couple to try now that I'll go through. So the 3 I want to give you are y equals cotangent x minus pi over 2. Then the next one is y equals tangent of x minus 2. And then the last one is y equals secant of x plus pi minus 2. All right, so why don't you try those 3? And I'm going to give you like a 3 count to pause and then we'll go through it. All right, so this one is cotangent x minus pi over 2. So it's inside, so that means it's going to be right pi over 2. So let me quickly sketch cotangent. So cotangent from 0 to pi looks something like this. So if we're going to shift it to the right, again, the strategy that we do is we're going to first shift the asymptotes. So we're going to have the asymptote at pi over 2 and 3 pi over 2. But then we basically have this. Oh, I shifted it the wrong way. All right, so forget that. Actually, it looks the same. Okay. So we had a vertical asymptote at 0. So that 0 asymptote looks like this. Yeah, so I said it incorrectly, and I was thinking about it incorrectly, but it turns out to be the same. And then when we have our asymptotes, let's see. This point is at pi. So this shape gets shifted to the right. And then this one also goes like this. And we have a repeating pattern, so we're going to get half of that pattern on this side. So that should be the graph that you get. All right, let's quickly, this one is going to be down 2 because it's outside of the function tan. So first let's sketch tangent. So tangent has a vertical asymptote at pi over 2, 3 pi over 2. And it looks something like this. Kind of wormy. Okay, and we're going to shift it down. And again, the way I like to do these is I know that these have kind of zeros along this axis, which is that I'm going to take this. I'm going to draw my axis way up here because I know I'm going down. My vertical asymptotes aren't going to shift because I'm just shifting downward, not left or right. But then my new axis is this. So I'm going to call this my new x-axis. And then that's my point. So right here, I had a 0 here, but that point gets shifted down, so I'm going to look something like this. And I have this point here, which was this. I'm going to have something that looks like this. And then a point here. And it looks like this. So that is what that looks like, kind of shifted down. All right, and the last one is secant, and we have 2. So we move left pi and down 2. So the question is, are we going to be able to fit this on the sheet? Well, that is a good question. All right, we'll do our best. So let's draw the secant function. So secant is 1 over cosine. So again, I know cosine looks like a cup. So I visualize kind of what it looks like, kind of kissing the cosine function and then doing this kind of happy, sad pattern. So there's my secant function. And I'm going to shift it left by pi. So here's the thing. It turns out that this thing repeats every pi radians. So shifting it by pi actually doesn't change. Well, does it change the pattern? Yeah, so I was just going to say it doesn't change the pattern, but actually it does change the pattern, yeah. In my notes, I made a mistake. So what happens is this gets moved over here. So instead of going up, it's going to go kind of downward. Shifting it by pi actually kind of does almost like a reflection. And then we're going to go down 2. Okay, so let's look at this. So the first thing I'm going to do is I'm going to look at my So let's say 0 is over here. Say there's 1, -1, -2, -3. I'm not sure we have enough room for this, but let's try to do it. So we have pi and 2 pi. Now our asymptotes aren't going to really change here, because the asymptote that was over here shifts over pi, is basically lines up with this one, and there's another one that shifts over here. So our asymptotes are basically in the same positions. The other thing, we're down 2, so I'm going to redraw my new x-axis. Quote, new x-axis. I may be the only person that actually writes this down, but that's how I think about it. And so we're shifting to the left. So before we had a point over here, we're going to shift it over here. So that's where I kind of ran out of room there. Here, we had a point here that gets shifted to the left, so we have something that looks like this. And then we're going to have another point over here. Okay, so hopefully you kind of can see that these parts over here got kind of cut off, but that's basically what it is. So for your homework this week, you just have to draw some graphs. So you have to draw the tangent, cosecant, secant, cotangent graphs, and then you have to do vertical and horizontal shifts of those graphs. That's pretty much what the homework is. All right, so I hope you're safe and doing well, and I'll talk to you next time.